For decades, humanity believed the moon was little more than a dead rock, a silent companion orbiting Earth, unchanging, stable, and predictable. But new discoveries are rewriting that story. At NASA's Jet Propulsion Laboratory, Ryan Park and his team uncovered something extraordinary, something that has baffled scientists worldwide. The moon isn't rigid at all. It's alive. It bends. It flexes. Using data from NASA's Grail mission, Park tracked two spacecraft, nicknamed Ebb and Flow, as they orbited the moon from 2011 to 2012. These weren't ordinary flybys. They measured the moon's gravitational field with precision so sharp they could detect shifts smaller than the width of a human hair. And what they found seemed impossible. The moon was moving, rising and falling by several feet with every orbit, squeezed by Earth's gravity like a stress ball in invisible hands. This phenomenon is called tidal deformation, and it's happening right now. As you watch this video, the moon is breathing in space, expanding and contracting in a rhythm set by Earth itself. But the real shock came when Park's team looked closer. The moon wasn't flexing evenly. The near side, the face turned eternally toward Earth, bent dramatically more than the far side. The pattern was asymmetric, strange, and utterly unexplained. The moon was hiding secrets beneath its surface. When spacecraft first photographed the far side of the moon in the 1960s, astronomers were stunned. The familiar side, the one humanity has gazed at for millennia, is marked with vast dark plains called maria, remnants of ancient volcanic floods. Smooth seas of cooled lava cover nearly a third of the near side. But the far side? A completely different world. Rugged, cratered, almost no maria. Only about 2% of its surface shows volcanic activity.
It looked as if the moon had two personalities, one shaped by fire, the other frozen in time. Scientists proposed theories. Maybe Earth's gravity focused volcanic eruptions on one side. Maybe the far side's crust was simply too thick for magma to break through. But none of these explanations truly fit. The asymmetry was too sharp, too strange. And now, Park's gravitational data revealed an even deeper mystery. The near side wasn't just different on the surface, it was different inside. Something beneath it was warmer, softer, more flexible. Something that explained why it bent more dramatically under Earth's pull. The moon, it seemed, was not the uniform sphere of rock scientists once imagined. It was a world with two faces, and two very different hearts. The answer lay deep inside. Beneath the near side, hidden in the lunar mantle, Park's team discovered something remarkable: radioactive elements. Not scattered randomly, but concentrated in massive deposits: uranium, thorium, potassium. Elements that generate heat as they decay, slowly releasing energy over billions of years. When the moon formed 4.5 billion years ago, it was born from catastrophe. Debris blasted into orbit after a Mars-sized world, Theia, slammed into early Earth. In that chaos, radioactive elements didn't distribute evenly. Instead, they accumulated beneath the side that would forever face Earth. The result? A natural nuclear furnace. A hidden heat source that kept the near side's mantle warm, soft, and pliable, while the far side cooled into rigidity. This radioactive heart explains everything. The maria seas, the asymmetrical flexing, the moon's two-faced identity. And here's the extraordinary part. That furnace is still burning. Right now, radioactive decay continues to generate heat, making the near side more flexible than the far side. Every 27 days, as the moon completes its orbit, Earth's gravity squeezes this warmer, softer hemisphere more dramatically, keeping the cycle alive. The moon, far from dead, is still internally active. To uncover these secrets, NASA had to attempt one of the most precise experiments ever conducted in space.
The twin Grail spacecraft, each the size of a washing machine, orbited just 55 kilometers above the lunar surface. Flying so low, they skimmed past mountains and craters, constantly adjusting to avoid disaster. They tracked the distance between them with microwave signals, accurate to a few microns, thinner than a human hair. Whenever one probe sped up or slowed slightly due to hidden gravitational variations below, the other detected the difference instantly. The result was a gravitational map so detailed it revealed features invisible from the surface: buried valleys, dense rock formations, even the flexing patterns caused by tidal forces. To make sense of it, Park's team ran the data through NASA's most powerful supercomputers. They accounted for every disturbance: solar radiation, thermal effects, even the tug of distant planets. Only then did the true picture emerge. The moon wasn't static. It was dynamic. It was flexing, bending, and shifting in ways no one had ever seen before. The moon wasn't the only body under the microscope. NASA applied similar methods to Vesta, one of the largest asteroids in the solar system. Scientists expected it to be layered like Earth, with a dense core of iron and lighter material above. Instead, the data revealed something shocking. Vesta was almost uniform throughout. No large core, no neat layers, just rubble compacted into a single mass. Then came Io, Jupiter's volcanic moon. For years, astronomers believed its eruptions came from a global ocean of magma. But gravity data told a different story. Instead of a molten sea, Io contained scattered pockets of magma, like hotspots beneath solid crust. These discoveries painted a picture of chaos in planetary formation. The solar system, once thought to have followed neat, orderly rules, now appeared violent, unpredictable, and asymmetrical. The moon's radioactive heart, Vesta's uniform rubble, Io's patchwork magma. Each contradicted old models and hinted that planetary bodies across the universe may be far stranger than we've ever imagined. For centuries, scientists assumed planetary bodies formed in stages, heavy elements sinking to create cores, radioactive materials spreading evenly, and heat dissipating predictably over time. But the moon's two-faced structure challenges all of it. It means the giant impact that created the moon was far more chaotic than models predict. Debris didn't settle evenly. Radioactive elements pooled to one side, permanently dividing the moon into hot and cold, active and dead. This asymmetry changes how we think about planet building itself. If our moon, born from a single collision, ended up so uneven, what about the countless exoplanets scattered across the galaxy? How many of them are lopsided, fractured, or shaped by hidden radioactive hearts? The moon's secrets ripple outward, reshaping our understanding of planetary science itself. These discoveries aren't just academic. They have direct consequences for humanity's return to the moon. NASA's Artemis program, which aims to land astronauts on the lunar surface and build permanent bases, must account for the moon's complex gravitational field. Without it, landers could miss targets by miles. Even more, the asymmetrical flexing creates stress patterns across the crust, triggering moonquakes. Future habitats must be built with these seismic risks in mind. But the radioactive furnace beneath the near side also presents opportunities. Regions warmed by internal heat might provide more stable environments for settlements, potentially even tapping geothermal energy sources. For astronauts, this isn't just about exploration. It's about survival on a world far more alive than anyone imagined. The image of the moon as a silent, lifeless rock is dead. In its place emerges something far more mysterious:
A dynamic world still shaped by an ancient cataclysm, still breathing under Earth's pull, still warmed by radioactive fire deep inside.
Every orbit, every tide, every hidden quake tells the same story. The moon is alive. It flexes, it remembers its violent birth, and it has never stopped changing. The question now is simple. If the moon, our closest neighbor, still hides such profound secrets, what else waits to be discovered across the solar system? The next time you look up at the moon, remember, it isn't just reflecting sunlight. It's flexing, breathing, and carrying within it the scars of a cosmic collision that still echoes today. What other secrets might be waiting, hidden in plain sight, above our heads?